everybody, and welcome to our next video. So for today's topic, we're going to be looking at our next derivative rule, which is called the chain rule. This is a really important one. So up to this point, all of the functions that we've dealt with have been non-composite functions, which basically just means our inputs are only based on x value. So for power functions or polynomials, those are something we never really have to worry about in the expanded form that we write them. But for all of our other functions, we have like trig functions whose arguments were only x, so sine of x, cosine of x. Our logarithms, it was only natural log of x or e to the x. So when we take those basic functions and we start to compose or put other kinds of functions inside of them, that changes how we have to attack or calculate the derivative. So that those kinds of problems require something called the chain rule. And it all has to do with because the fact that they are composite functions. So that, or again, to remind you, a composite function basically just means two functions have been combined to make a new function in a way so that one of the functions was substituted into the other. Or in terms of domain and range, when we have a composite function of the form f of g of x, or you may have remember the fog notation, this little open bullet symbol is another way of representing this composition. So we read this as f composed with g. So what that means is we have an x value as an input, so we pick some value of x, and we substitute that into the g of x function, and that produces some kind of output value for g. But whatever that output value is then substituted inside of the f of x function as its input. And that is how we ultimately get to the final result. So it's not a value of x being directly substituted into f. We have this little stop in the middle. So when that happens, we have to take into account how everything changes, how x changes, how g of x changes, and how the outside f of x function changes. So to help us with that, we're going to go through a little exploration here. So I've got a big table here, and this table has four composition functions. So the first thing we're going to do is look and see how they're composed. So we're going to break them apart into their pieces, their inside and their outside. So when you're trying to explore inside and outside functions with compositions, a lot of functions have natural insides. So trig functions all have an argument. They have to be sitting inside those parentheses. That's what we take the sine of or the cosine of. So if that inside part is anything but just x, then we know it's a composition. So whatever that new thing inside the argument is, that would be our inside function or our g of x. Other natural insides or natural input locations, exponential functions. Normally, it would be read as, or you would see e to the x. So that exponent spot, that's the whole reason why we name it an exponential function, because that's where a variable sits. So if that is changed to anything but just x, then we know we have a composition. Logarithm, same idea. Normally it would be natural log of x. That x location is our argument. So if that is anything different, then now we have a composition function. Radicals, same way. Radicals have a natural inside, the radicand, or the inside of the square root symbol. And even sometimes polynomial functions. When we have a polynomial raised to an exponent, well, inside of the parentheses, that is an inside. So if this was not just x to the n, but instead we change it to a group of terms raised to the n power, now we have an inside. So keeping all of those things in mind really helps us look at these new, more difficult functions and analyze what's inside and what's outside. So let's try that. So for the first one, h of x equals sine of 2x. Again, it's a trig function. We have a natural inside, and it no longer says just x. So the outside function would be sine of x. That's how it would normally be written if it was an easy problem. But instead of sine of x, we took 2x and plugged it into where x used to be. So that's how we break this apart. Second one, h of x equals the quantity x cubed plus 2 raised to the second power. Well, our inside is pretty obvious here. It would be what's inside of the parentheses. But if we didn't have a group squared, then remember it would be just x raised to that power. So that is actually my outside function, just simply x squared. Third one, h of x equals e to the x squared plus 2x power. Again, that one is pretty straightforward. Our inside, if you notice, sometimes it is actually easier to identify or write down the inside function first, and then once that has been removed, that empty spot just gets filled back in with x. So that is a strategy sometimes if you're struggling with this. Pull out the inside thing and then replace it back with the normal input of x, and that is your outside function. And then the last one, h of x equals natural log of sine of x. My inside, the argument there would be sine. If I took that out, put x back in its spot, we would have natural log of x. So the reason why it's important for us to be able to identify both of these is because both things in the function are going to make some kind of contribution to its derivative. Because if we were just dealing with a sine of x function, then we know its derivative is cosine. So that's the kind of pattern that its slopes would have. But if our inputs are not just x and they're actually 2x, well, that has a different derivative. Derivative of 2x is 2. So we have to account for both of those. So that means our inputs are changing based on a pattern of 2, and our outputs are changing based on a pattern of cosine. So we have to be really careful here, okay? So we're going to do this for all three of these. So our f prime for x squared would be 2x. That's how this pattern of y's changes. But our inside would be 3x squared because that's how the inside function changes. Next one, e to the x changes based on the pattern e to the x. X squared plus 2x would change based on the pattern of 2x plus 2. Natural log of x. That derivative is 1 over x, but sine of x, its derivative is cosine x. All right. So now what we're going to do, we're going to come up with some values here. So for each one of these, I've picked out a value of c, and we're going to use that as an input to these four functions. And what I'm going to do at the end is I'm going to show you the connection, or we're going to kind of try to discover the connection together. So I'm going to real quick go through and fill out these values, and then we'll come back together. All right, so there are my table of values. I've got the four numbers filled out for all of these. But now what we need to do, this fifth column here, I want to find out what is the value of f prime. So this column, when I take the value of g of c and plug it into that guy. Because if you think about it, whatever the inputs for f were the first time go around, and really remember, these guys were inputs for f. Remember, we know that from past experience, the inputs of the original function need to be the inputs for the derivative function as well. So it kind of makes sense that we need to know what the value of g of c is when it's plugged into f prime. So that's one part of this. So let's do that together here real quick. So I'm going to take this value, stick it into f prime. So when g of c is 2 pi, I want the cosine of 2 pi, which, remember, on the unit circle, 2 pi would be all the way around. That x-coordinate is 1. Then for the second one, I'm going to take 29 and stick it into 2x. So 2 times 29 is 58. Next one, when g of c is 3, I'm going to stick that into e to the x, so we would get e cubed. And then for the last one, when g of c is square root of 2 over 2, we need to stick that into 1 over x. And remember, that's really like multiplying by its reciprocal, or really just flipping this guy. So we get 2 over root 2, which when we actually simplify that all out, turns out to be square root of 2. All right, so now what we're left to do is try and put all of this information together and figure out what the true value of the derivative of these original functions at these values of c are equal to. Well, I, with the power of calculus, know these answers, so I'm just going to go ahead and tell them to you guys. So the slope, or the rate of change of sine of 2x at x equals pi, is actually 2. The slope of this function, which is actually a sixth degree polynomial, once I multiply all this out, at x equals 3 is actually 1,566. The slope of this e to the x squared plus 2x function when x equals 1 is actually 4e to the third power. And then the last guy, the derivative value of natural log sine of x at x equals pi over 4 is actually just 1. So those are what the answers are, and the information needed to create that column is somewhere in this table. And so what I'm going to give you guys a few seconds to do is look at this column, look at the values that I just gave you, and then go back and look at all the information and how we broke it apart and see if you guys can't piece together on your own how it is I created these values from all this information that we found. So take a few seconds, think about it. When you're ready to hear the answer revealed, then start the video back up and then we'll talk about it together. So I'm sure you guys all pieced it together by now, and if not, at least you got to see a cool little turtle in the ocean. Um, but to find the value of h prime of c, to evaluate this function's derivative at these values, all we had to do was take these two columns and multiply them together, which means we have just discovered the chain rule. To find the derivative of h prime of x, we simply have to take the derivative of f prime, still composed with that same inside function, so f prime composed with g of x, but then we also have to account for how that inside function is changing, which is why we didn't just take this value, we had to multiply it by the value of the inside function's derivative. So we will multiply by g prime of x. That is the definition of the chain rule. So I'm actually going to rewrite it down here. So to find the derivative of f of g of x, we take f prime of g of x and then multiply by the derivative of the inside. Now, you may be wondering to yourself, what the heck does that look like? How do I find the derivative of this composition function? Well, it's easier than what you think. I'm gonna show you guys a strategy to help identify all these pieces and then put them all back together. So I'm gonna break it apart and then put it back together in the end to find the derivative. But the really important part that you guys need to understand is how the chain rule works because it's a composition function. So when taking the derivative of a composition function, you have to make sure that we account for the change that occurs in every part of the function. So when a function is composed of two different functions, each one's change has to be present somewhere in that derivative. So the easiest method that we have for doing this is called U substitution. Now you've used U substitution most likely back in pre-calc when working with trig functions that were in alternate forms. So mainly when we have a trigonometric equation that's in the form of a quadratic equation. We used U substitution to take out the hard part, which was the trig parts, and then replace them with a simple variable U, and then you could do whatever factoring or solving that you needed it to do. So we're going to still do that same process, but now after we replace the difficult stuff with U, we're going to use it to do calculus. So we simply rewrite a composite function as a simple function by replacing our inside with our U. So when we identify our inside function or the g of x, instead of writing it as f of g of x, we're going to pull that out and make it f of u. And then we will take the derivative of that result. So when I do that, I get a little simpler version of this, f prime of u times u prime, or the derivative of that inside function. So again, just pulling out the difficult stuff and replacing it with something as simple as a variable just makes our job easier. So again, doing some algebraic manipulation to make the calculus easier. Common theme with a lot of this. Now, why does it work? Well, it works because of this little proof here. So we're going to start with a very basic one. So I have y equals 3x plus 5 quantity squared. So this is really a quadratic function because it's something squared, but it's composed with a linear function. So that means there are two kinds of change. We know that quadratics change based on a linear functions pattern, and then a linear function changes based on a constant functions pattern. So we have to make sure that both of those things are accounted for when we find their derivative. But our inside function is u equals 3x plus 5. So again, we're going to take the inside part and just simply swap it out with our variable u. In doing so, I end up rewriting that as y equals u squared. Well, that's a really simple function to take the derivative of. But technically speaking, now I'm about to do and show you guys some stuff that we will not do on a daily basis when we do these problems. This is strictly for the proof of why this works, and then we're going to do it in a much easier way to wrap your head around when we actually write it out. But when I go to take the derivative of an equation that says y equals u squared, notice that this isn't d dx because the way I have it written, it's not a function that depends on the value of x, it depends on the value of u. So we make these match up. So if I du this equation, then I still use the same rules. That would be a power rule. It's just everything's in terms of u. So instead of dy dx, it's actually dy du equals 2u. So that is showing how this quadratic function on the outside changes based on a linear functions pattern. Now, technically, these quantities in this notation, dy and du, they're called differentials. They're actual quantities that I can manipulate and move around in an equation and separate if I want to. And in this case, I want to. So for right now, I have this equation that says dy, the change in y, is equal to 2u times the change of u. So we're going to leave that guy alone for right now. And now we're going to go and look at our inside function. So the inside function, we need to be able to explain how that guy is changing. Well, u is equal to 3x plus 5. So u is now a function of x, which means to take its derivative, this is where I would do d dx. So notationally, instead of dy du like we had over here, it follows the same kind of format, but we write it as du dx. The derivative of the linear function 3x plus 5 is just 3. It's a constant rate of change. So just like I did before, I can manipulate these differentials and I end up with the equation du equals 3 dx. Well, if I take this piece of information and bring it on over here and replace that du with what I know du is now equal to, and I go back and take what I know u to be equal to and replace it in this equation, now I can go back and write the final form. So when I do that, I get 2 times what my u was equal to times what du is equal to. Or once that's all in there, if you notice this dx quantity, I can now move that guy back over to end up with the notation that I would want, which is dy dx. So that seems like a very convoluted process, but if you really think about what we did, we started by taking out the hard stuff and replacing it with u. Then we did the calculus in terms of u, and then we just put the complicated stuff back in at the very end. That's a very similar process to what you guys did in pre-calc with u substitution, and it's a very helpful process. So by the end of this, if you really look at what we have here, it kind of has that same structure. Again, this is like saying y is equal to f of u. And so by the end, what I have here is f prime of u times u prime. F was a quadratic, so its derivative is 2u. That's what this is, 2 times u. And then the derivative of the inside, or u prime, the derivative of 3x plus 5 is that extra factor of 3. So the easiest way to wrap our head around this is going to be this notation, and that's how we're going to set up most of these problems. But the biggest thing to remember with chain rule, when you're taking the derivative of a composite, is don't forget to find the derivative of the inside. We always have to have that extra factor for u prime at the end of our answer. All right, so let us try some. Now, some of these right off the bat, you're not even going to be able to recognize that it is a chain rule. And those are the hardest ones. Those are ones that you're going to have to really train your brain to look for because the other ones are easy. They're very recognizable, like the ones from the exploration at the beginning. So the ones that are not as obvious, you may try something and it may fail. So for example, this first one I chose for a reason because most people look at this and don't recognize this as a composition. Y equals 1 over the quantity x plus 1. This is actually a composition. It's just not easily recognized as one. What most people will look at this and instinctively think is, oh, it's a fraction. Let's do quotient rule. So let's say that we explored that option. Top function is 1, its derivative is 0. Now, if you've trained yourself well from the previous section, then you should have gotten a little alert that was going off in your head. He said, don't do it if you get a derivative of 0. And that's true. Because if I continue with this, and I can keep going with this problem, I get 1. And I can do the quotient rule. So insides minus outsides all over the original denominator squared. So we can do it that way. But because we got a derivative of 0, it means that this is probably not the best way to do it. Okay. So what this really is the quantity x plus 1 raised to the negative first power. So that's something that I don't think we've seen up until this point in this course, where I've taken an entire denominator and moved it up to the top and put it as a group raised to a negative exponent. But that is a strategy that we can use to rewrite any rational function. Now, I wouldn't advise doing it this way, but if I had something like x plus 2 over x plus 3, technically speaking, if I really wanted to, not that this would be advisable or a good idea, I could actually write it like this. I can bring this whole denominator up top and multiply by it. But if I do that, because I moved it where it doesn't belong, it has to have that negative exponent attached to all of the stuff that I moved up. So that entire group. Now, doing it in this case, this is the most common way where this is mistaken, because this isn't a group already raised to a power. Now, if I had this as quantity squared in the denominator already, then it's a little bit easier to recognize because of the parentheses. But when that denominator doesn't have parentheses and a power, just know that I can always pull it up top and give it the negative 1 power. This allows me to recognize that my inside would then be the inside of our parentheses. So I'm going to identify my u as x equal, or excuse me, x plus 1, and then I'm going to take the derivative of that. I'm going to find u prime. So technically, we could use the du dx notation like the proof did, but that proof, moving all those parts around, it's a little bit unnecessary because we always know what the result's going to be. So it's actually a little bit easier to use this u prime notation. So in this case, my derivative of x plus 1 is just 1, and sometimes that will happen. So this is still a composition because u is x plus 1, or if we think about it in terms of the f of g of x, my outside function here is actually the parent rational function 1 over x, and my inside is that linear x plus 1. So we can still break those pieces apart. So what I'm going to do now is rewrite the original in terms of y. So this is really, or excuse me, in terms of u. So y equals u to the negative first. And now we do calculus. So even though this is in terms of u, I'm still going to just write dy dx for right now, because again, in the end, I'm going to replace u with x. So using the power rule, this becomes negative 1 u to the negative second. And my recommendation to make it easier for you guys to write is leave everything in terms of u until you are totally done with the math, and then just make that substitution back in at the very end. So for example, I could plug x plus 1 back in right now, but it's not finished because I need to get rid of that negative exponent. So instead, I'm going to fix it and make it in the total final form. The only thing I have left to do now is stick x plus 1 back in here. So I get a derivative of negative 1 over the quantity x plus 1 squared. That is the derivative of 1 over x plus 1. All right, let's try another one. Again, we're always trying to think of what is the inside of the function. Identify our u first and then rewrite. That makes it easier to find the outside. So in this case, my inside of the argument would be x cubed. We can go ahead and find u prime. Oh, and I'm so sorry. Let me go back here. Not that it's a big deal, but or it is a big deal. Um, I forgot the U prime. I forgot to do the chain rule. So the big red flag that I told you guys not to forget, I actually forgot. My bad. So uh, we did the derivative with respect to U, and then again we have to remember the U prime. The reason why I said it's not a big deal, even though it is because in this case our U prime's value was just 1. So realistically, this is going to be U prime, or I can actually put this in the numerator of this fraction. It's just in this case, this is what happens when you do this for a really long time and you can do these in your head. I knew that the u prime was just going to be 1, and so we would still end up with that negative 1 in the numerator. But you guys, when you're learning, always make sure that you have that u prime in there. And fingers crossed I won't forget and have to redo this video. So for the next one then, our our inside is x cubed, so then my u prime would be 3x squared. So I got all the pieces I need. So now I'm going to rewrite the original. This is really y of tangent of u. So the derivative of tangent we know to be secant squared. So this would be secant squared of u. Again, that in the form of our derivative, that represents that f prime of u. It's the derivative of the outside function, but we keep the same inside as the original. Now we have to multiply by that u prime, and I'm not going to forget to do that this time. Okay. So there's not really any simplifying to be done in this one, but what I am going to do when I replace, again, I don't like these extra things hanging out after the argument of the trig function. So I'm going to put my u prime of 3x squared out in front and then multiply it by secant squared of my argument, which was x cubed. And remember, parentheses around that argument when it's not just x helps everyone understand where the argument ends. It keeps everything looking real nice. So that is our derivative. Again, it changes based on the pattern of secant squared for tangent, but also changes based on the pattern of x cubed, which is that 3x squared. All right, let's try a couple more, a little bit more difficult now. So the next one, we've got a big radical. So that one is a little bit easier to recognize the inside, but the inside is a bit bigger here, so it is a little bit trickier. But my inside, 3x squared minus x plus 1. So then u prime would turn into 6x minus 1. So now I'm going to rewrite my original. So I get y equals u to the 1/2. I'm going to take my derivative, so dy dx. And again, that we treat these just like we would x's as far as taking the derivative of the u stuff. So derivative of x to the 1/2 would be 1/2 x to the negative 1/2. But because it's a u, we need to make sure that we use u. And because it's a u, we're going to multiply by u prime. So if I clean that up, again, do as much work in terms of u so you don't have to write. Because if I go to replace all of this stuff now with all the x stuff and then fix it, then you have to write all these long expressions out over and over and over again. It's just faster and easier for us to keep it in terms of u until it's totally done. So that means I would end up with u prime over 2u to the 1/2. Now we can go ahead and stick everything back in here. So my u prime is 6x minus 1, so that goes in the numerator. And then on the bottom, I have 2. And with fractional exponents, anytime that your argument or the u is more than one term, you guys have a choice. You can go back to your radical symbol, but if it's anything beyond 1/2, if it's like 3/2 or 5/2, then you're going to want parentheses and your exponent on the outside. So it's kind of a personal preference. Most of the time, I will go back to radicals when it's just the 1/2 or 1/3 power. But if that numerator for the exponent is anything besides 1, then you're definitely going to want to use the fractional exponent form. So that is it for this guy. If anyone's looking at this and wondering, well, can't you reduce this 2 out with that 6? Remember, can't reduce factors of the denominator out unless it's a factor of all the terms in the numerator. And if this was -4 instead of -1 or any other even number, then yes, we could reduce 2 out from everything. But just because the 6 and 2 reduce doesn't mean the whole thing does. So you got to be careful with that. All right, and then this next one, this one's a little trickier because some people may look at this and not realize that this is a composition still, because most people, when they see trig, are only going to focus on the argument, and they're going to look at that and say, well, that's just tangent squared of x. There is nothing else in the inside besides x. When you set up the chain rule, if you set up u equals just x, no other terms being added or no coefficient or anything like that, then u prime is always just 1, and there's really no need to set it up that way. So odds are that's probably not the right value for u. So this is a special one that you guys need to be on the lookout for. Whenever we have a trig function raised to a power, there is another way of writing this, and we talked about this previously, where we write it as the trig function inside of parentheses, and then that power is technically sitting on the outside. So rewriting in that form will actually help you realize that our inside function in this case is actually the tangent of x function. The outside function is actually the quadratic. So when I rewrite this guy, it becomes u squared. So if u is tangent of x, then my u prime is secant squared x. So I already have it rewritten in form of u, or in terms of u. So now dy dx would give me 2 times u prime. There's no simplifying that we need to do there beyond what's already done. So in this case, when I go to rewrite it, we end up with 2 times my u, which was tangent of x, times my u prime, which is secant squared x. And that's it. So again, that's a special one anytime that you have a trig function raised to any power besides just one. So if there's any number up here, it's automatically where this is a power rule problem. That's our outside function is a power rule. And then the inside is that trig function itself. All right, so now that we've seen a couple of examples of this chain rule being used, what we can do now is actually go back to all of our basic rules and reframe them with the mindset of working with composition functions. So we take the old school power rule, which said d dx of x to the n equals n times x to the n minus 1, and now we can rewrite it as the general power rule. So the previous one only applied when it was just x to a power. But now if it's any function raised to a power, now we can actually write it or use the chain rule to find its derivative. So that's why we call this the general power rule. So it's basically everything reworded in terms of u. So there are two forms of this. Some textbooks use the du dx notation. I personally prefer to use u prime. So this is the one that you guys are going to see me use most often in class and in these videos. But it still works the same way. Essentially, we're just going to take the old power down. The base still stays the same. Instead of x, it's whatever that function is. The new power is n minus 1, but then we have to remember the derivative of the inside and multiply by that u prime. So what this is again, it's just another shortcut. So my recommendation is until you get really, really good at the chain rule, I still recommend that you guys identify u, find u prime, rewrite it, and do it all that way out. So I'm going to do that way first. Okay. So u in this case inside would be 3x minus 2x squared. U prime would be 3 minus 4x. The function can be rewritten as u raised to the third power. So then its derivative, f prime of x, would be 3u squared times u prime. So again, this is really what this rule is saying. So then we can replace all the u's with what it's equal to. So that would give me f prime of x equals 3 times my u, or 3x minus 2x squared, quantity squared, and then multiplied by u prime, or 3 minus 4x. Now, because we have a binomial squared and then this extra binomial, if you chose to, we could actually pull this 3 into those two pieces or those two terms, and I can actually rewrite this as 9 minus 12x and then multiplied by this group. Oops, forgot the squared on there. So that is our final answer. Okay. Now, again, that is if I want to do this the long way. And again, I highly, highly recommend that you guys stick to this format and follow that structure so you know for sure you didn't miss anything. Now, part of being a good mathematician is being efficient. So once you've mastered this concept and you feel extremely comfortable with it, then you could start to do a little bit more mental math and using this shortcut. So again, I've been doing this a little bit. So when I look at this and I see this group in my brain, I am reading this as u cubed. Oh, that's not a u. Sorry, sure what my pen did there. U cubed. So I know in my head the derivative of u cubed is 3u squared u prime. So in my head, I'm doing a little bit of mental math and I'm saying, okay, I need to bring down the old exponent, 3. I'm going to multiply by the same base because that is my u. New power is 2, but then I multiply by the derivative of the inside, which looking at that gives me 3 minus 4x. And then from there, we can simplify it and we get this same process or same final result. Again, I'm not advocating for any of you guys to jump right to doing it this way. You've just now learned chain rule. and you need some experience with doing it this long way and breaking everything down to understand the structure and really master it. But eventually, you guys are going to be so skilled at this that we will be getting to this place and you can do it pretty rapid fire. Okay, let's try another one. So g of t equals -7 all over the quantity 2t minus 3 squared. So we're going to rewrite this guy. Again, the form that it's in right now, quotient rule is not it is an option, but it's not the correct option because the derivative of the top would give me 0. So there must be some other way to do this. And that other way is moving that group into the numerator with a negative exponent. So now that provides me with my inside function. So my inside function would be 2t minus 3. U prime would be 2. When I rewrite this, I end up with -7 u to the -2nd power, and that makes g prime of t bring down the -2, so we'd have positive 14 times u to the -3rd times u prime. So one thing to remember with these negative exponents, the only thing in this expression with a negative power is this guy. So that means when I move it to the denominator where it belongs, everything else stays in the numerator. So you have to be very careful with that. So this is really 14 times u prime all over u to the positive third, or when I replace everything, u prime is 2, so that numerator will yield 28, and then the denominator is this binomial cubed. So that is our final answer. All right, one more. This guy gets a little bit more difficult. So we're going to differentiate f of x equals x squared times the square root of 1 minus x squared. So just reading that, I know that it is a product rule because I said times. I'm taking one kind of function, a power term or a polynomial, times a radical. So x squared, that derivative is 2x. Second function, 1 minus x squared, that actually requires a chain rule. So when you are doing the chain rule inside of the product or quotient rule, to help us stay organized, my recommendation is we're going to take this and do some math off on the side. Okay. So I'm going to pretend like I have the function y equals square root minus 1x squared on its own. This is a separate problem for right now. If I did, then my inside here would be 1 minus x squared, and u prime would be -2x. So then I can rewrite this as y equals u to the 1/2, and therefore dy dx would be 1/2 times u to the -1/2 times u prime, or dy dx equals u prime over 2u to the 1/2, or dy dx equals -2x over 2 square roots of 1 minus x squared. Or looking at that, I know that's going to reduce even further because there's a common factor of 2 in top and bottom. So I do all that work off to the side so that I don't have to try and do all of this stuff in this little spot and end up with a bunch of lines underneath of this. And then it makes me reading my product rule information way more difficult. I like to keep that same structure and keep all my work organized. So my fourth line of the product rule stuff is -x over the square root of 1 minus x squared. Again, it's really helpful for me. I know I'm a sloppy person when I'm writing, so the more I can do to help myself stay organized, the better off I'm going to be. So now we can do insides plus outsides. So f prime of x will give me 2x times the square root of 1 minus x squared. And then normally it would be plus, but I do have a negative in here that I'm multiplying by. So I'm going to make this minus x times x squared. Remember, if I take a non-fraction times a fraction, I can really think of this as x squared over 1. So it's really just like x squared is getting multiplied by that numerator. So that yields x cubed over the square root of 1 minus x squared. Now, there are lots of problems like this, especially when you have a product rule where one of the factors is a radical, but the other one's not, where there's a common simplification that occurs with the derivative. Because what happens when one of the factors is a square root function, you always end up with one of these being a fraction with a radical in the denominator. The other is just the radical on its own. So what ends up happening is we want to get a common denominator for this guy. So right now this is over 1. So to get that common denominator, we actually have to multiply this first term, top and bottom, by this radical that is in the other guy. So we're going to multiply top and bottom by 1 minus x squared. In doing so, these radicals are actually going to cancel each other out because the square root of a times square root of a is square root of a squared, or a. So what we're actually left with is just 2x times the inside of that guy. That is what's left in this numerator. And then we're going to have minus x cubed from the numerator of the second fraction, and all of that will be over that common denominator of 1 minus x squared. That would be our derivative, and now we can simplify that. So I'm going to distribute the 2x inside, so we get an f prime of 2x minus 2x cubed minus x cubed over our radical, or 2x minus 3x cubed over the square root of 1 minus x squared. That would be the best simplified version. You could tell writing that in one fraction is definitely an easier form to work with than the separate terms that we started with after the result of the product rule. So that would be an example that is definitely more difficult than these first few examples. But as far as the chain rule goes, the chain rule was actually just one fairly simple part of this process. So you guys can see the more rules we learn, the more steps these problems can end up having because we just start to combine rules on rules on rules on rules. So that's where they start to get really, really fun and interesting. All right, so now we can actually go back to all of the other rules that we've learned so far. And basically now these are just general forms for any of those rules. So again, up to this point, we saw derivative of sine of x is cosine of x. Now derivative of sine of u is cosine u times u prime. So that's really all we did to all these guys. We replaced the x's with u's, and because of that, we have to multiply by u prime at the end of every single one of these rules. So the only rules not listed here are the base A and log base A, but we're going to take a look at some of those later on. But again, those follow the same process. It's just instead of x's, we have u's, and then we multiply by u prime. So it's a fairly simple format for really all of these guys. So now I really just want to dive in and try some examples for these. So again, keeping that same structure and format, it's really helpful when we start combining stuff. So identify my inside. In this case, my inside function would be e to the x. Its change is represented by e to the x. That's the derivative rule. So then my original function I can rewrite as cosecant of u. So derivative of cosecant of u, again, the general rule up in the top of that table. It's a c function, so I know it's negative. So this is negative cosecant of u times cotangent of u. But then we multiply by u prime. Now we put our u stuff back in. There's not really any simplifying to be done. The only thing that I advise is, again, this is a non-trig function, so I'm going to move this guy to the front. I'm not going to rewrite this line with that there because I already have to do some swapping anyways. So I'm just going to do that when I rewrite. So u prime goes out in front, so this becomes negative e to the x times cosecant of e to the x. Don't forget your parentheses around that argument. And then times cotangent of e to the x. That would be our answer. That's our final derivative. Okay, next one. Y equals cosine of x squared minus 3. So my u, my inside, again, these trig and exponential functions and logarithms, they have these natural interiors or natural arguments. So it makes it a good bit easier to identify that u. So we're kind of just looking for what's inside of that argument location. So in this case, it would be x squared minus 3 for my u. So then u prime, its derivative would be 2x. So when I rewrite the original, this is just cosine of u. So dy dx would turn into, again, it's a c function, so the derivative is negative. Cosine turns into sine of u, so that argument always stays the same, and then times u prime. That's probably one of the most commonly made mistakes is students want to change the argument because you change the function. But remember, the inside always stays there. Whatever that inside function is, it's always going to stay the same no matter what. Now that we have the derivative in terms of u, again, now we can just replace everything. Again, the only really simplification that can be done here is when we replace stuff, I'm going to go ahead and move the u prime out in front. So we end up with dy dx equals negative 2x times sine of the argument x squared minus 3. Okay. Now for our last one here in this batch, we've got y equals 3e to or e to the 3x. This one's pretty straightforward and simple. Again, for exponential functions, our u is always going to be the stuff sitting here in the exponent because that's normally x. We changed it to 3x. So u is 3x, which means u prime is 3. So if y is equal to e to the u, then dy dx is equal to e to the u times u prime. So, and again, this is another one where it's not that we have to move u prime out in front. It just looks weird to multiply by a constant multiple behind something. So when you have factors that are just numbers, those constant multiples or coefficients, always just put them in front. So this will just become 3e to the 3x. And that's it. So those three weren't too bad. Again, you sticking to that structure of identifying u and u prime, rewriting, do the calculus, and then rewrite again. That format is extremely helpful, and especially for one like this bad boy. This one has a lot going on. So if you notice right off the bat, I have sine cubed of 4t. Now I could have parentheses around here, probably should. But the fact that I say sine cubed should be a red flag. We saw one like this a little while ago in this section where it was tangent squared. And I told you anytime that a trig function is raised to a power, that this is really rewritten as the trig function, or in this case, sine of 4t, all raised to that power on the outside. So keeping that in mind, my inside function here is sine of 4t. And then to find the u prime, then we run into an issue. So before we do that, I want to rewrite the original function. So right now, I am trying to take the derivative of y equals something cubed, or u cubed. So now that I have it in that form, now we can come back. I've got u equals sine of 4t. But the issue here is this function is not one of the basic rules. This is a sine of a something else. It's not just sine of t or sine of x, it's sine of 4t. So this is actually a double chain rule. These show up a lot with trig functions raised to powers where the arguments are not just x or t or theta or whatever it is. But they show up quite often with trig functions, but this is the typical format for one of these. So what do we do? Well, if this was just its own standalone problem, had I given you just y equals sine of 4t, well, you would have set up the chain rule where u is 4t and then found its derivative. So nothing changes. The only thing that's going to change in the process is how I'm going to rewrite this. So when it's a double chain rule, we already identified what u is going to represent. So I don't want to define u somewhere else on my paper because that's kind of misleading or confusing. So instead, what I want to do is I just pick another letter. U is just kind of an arbitrary value that's used to replace stuff because it's typically not a variable used in a lot of problems. So I'm just going to pick something else. Typically, when I do these, if I have to do a double chain rule problem, I like to pick V. So I'm going to let V equal the inside of this sine function. So that would be 4t. So the ultimate inside of this guy is 4t. I like to call this a turducken. If you never heard of that term, some people make them on Thanksgiving. It's a turkey stuffed with a duck, stuffed with a chicken. It's a turducken, something inside of something inside of something. I got 4t stuffed inside of sine of 4t stuffed inside of u cubed. So you have all that broken apart. Now we're going to start with the very inside with the chicken, uh, or v, and then work our way back out. So once we know the very inside is 4t, then its derivative v prime would just be 4. So then we're going to come back to this guy. So before I can find u prime, we're actually going to rewrite this. So by taking 4t out, then v would go in. And now I'm going to take the derivative, but in terms of v. So the derivative of cosine of the derivative of sine of something is cosine of that something, but times v prime. And then I can rewrite this guy. So cosine of v gets replaced. So this would be cosine of 4t times v prime 4. So I'm going to put that guy in front of here. So we get 4 cosine of 4t. So we have our u prime. So these middle steps are really just necessary for us to get the difficult stuff out of the way so we can do the calculus. So just like we do with the original. So now I'm going to go back to the very original guy, take its derivative. So u cubed turns into 3u squared times u prime. Now we can replace all of our u stuff with what we know it's equal to. So u becomes sine of 4t again. So this is really going to become 3 sine squared of 4t. And then times u prime would be all of this. So times 4 cosine of 4t. And then the only thing that we have to do here is because we have two factors that are constants, we're just going to group them together out in front. So all of this, excuse me, not dx. Sorry, I forgot this guy's in terms of t. So these should be dy dt's. Sorry about that. So dy dt will be equal to 3 times 4. We group them together to make 12 times sine squared of 4t times cosine of 4t. And that's it. So that is our first turducken. I can guarantee you guys will see another one of those at some point. So again, just breaking it down inside by inside by inside, it really helps to keep all of that stuff organized. Now we're going to take a look at a few examples using the general form of the natural log derivative rule. So for this first one, it does look like it has the form of natural log of u, and we could actually proceed with this problem in that format. So if we wanted to, our inside function would be 2x, and then u prime would be 2. So then when I rewrite this as f of x equals natural log of u, the derivative of that is always going to be of the form u prime over u. So if you go back and look at the table up here, it's written in two ways. So this is a common way so that you see the u prime separated. But realistically, it's going to be more efficient for you guys just to get used to writing it in this form, the u prime over u. Because when we get to content later on in the course, this is the form that its derivative is going to be recognized, and it's going to help us actually work backwards through that. So this is how I'm always going to write it. So just so that you guys get used to it, u prime over u. And so if I replace that with the u stuff back in there, I get 2 over 2x, but then that needs to be reduced. So we end up with just simply 1 over x. And if you think about it, that is actually tied back to a problem that we saw a few sections ago. This natural log function, remember, a product inside of the argument can actually be rewritten as the factors of the product separated. So this can become natural log of 2 plus the natural log of x. And remember, doing that, this guy is really just a number. Natural log of 2, if you type it into a calculator, you're going to get a decimal value. So because of that, when I take the derivative, that guy just disappears, and we're just left with the easy natural log rule, derivative rule, which is just 1 over x. So remember that any function of the form natural log of c times x, all of those functions are going to have a derivative of just 1 over x because of this. And so really, no matter what that number is, if you do it with the u method, that c value is always just going to cancel each other out. So uh, either method's fine as long as you guys build up a routine and you know how to work with it. So for any natural log problems not of that form, then it's always going to be setting it up with our u's. So f of x equals natural log of x squared plus 1. So my inside, again, it's just the argument of the log. In this case would be x squared plus 1. So then u prime would be 2x. So the one nice thing about this, you guys are going to be able to pick up on the process or the form of this derivative much faster than really any of the other ones, because every time that I rewrite it as natural log of u, it's going to always have that same form, u prime over u, and then all these guys are just going to fit right back in. So this is one rule that students tend to pick up very quickly. It's just a matter of memorizing that form of u prime over u, and then try to simplify if anything does, but majority of the time it will not, unless we're talking about a constant multiple like the previous problem. So that's it. 2x over x squared plus 1 is that function's derivative. So this next one, f of x equals x times natural log of sine of x. So this is a product rule, but it's going to require the chain rule inside of it. So first factor is x, its derivative is 1. Second factor, natural log of sine of x. Its derivative would require a chain rule, so I'm going to do that math off here to the side. But again, I'll show you guys in a second here how we can really build up towards that um, idea of being efficient mathematicians here. So looking at this, my inside u would be sine of x. U prime would be, oops, sorry, will be cosine of x. So then this is really y equals natural log of u. So y prime will be u prime over u, or we get cosine over sine of x. And that guy is actually using a trig identity, the same thing as cotangent of x. So that is actually the derivative here. Now, as we build towards that process of being efficient, again, this rule is one of those that's really easy to pick up on. So because of that, a lot of times you guys are going to be able to look at this and easily identify what my u is. So if it's just a matter of doing some scratch work off to the side, we know that this derivative is going to yield our u prime over u. So when we are able to do mental math with these, I know that sine of x is going to go on bottom and its derivative cosine is going to go on top. And so we can kind of piece all that together and realize that we're going to end up with that cotangent function. So now it's insides plus outsides. I don't need to rewrite anything because I've already done that off here to the side. So we end up with f prime equals natural log of sine of x plus x cotangent of x. And that is it. Now for the last guy, this involves natural log, but it's not a actual natural log function. So when we were to look at this guy and really classify it as to what kind of function it is on the outside, this is actually a power function or a cubic function whose inside is natural log of x. Again, we want to think about the outside function, or sometimes it's easier to identify the inside by looking at the parentheses. So in this case, our inside is natural log of x, and its derivative is 1 over x. When I rewrite this function, the outside piece, when I remove my inside, leaves me with u cubed. So the main derivative rule here is the power rule. So I get 3u squared times u prime, or in this case, that would leave me with 3 times the quantity of natural log of x squared times 1 over x. And the easiest way to rewrite that is 3 times the natural log of x quantity squared all over x. Now, I'm sure some of you are wondering about this power of the natural log. It's easy to get mixed up with this. One of the properties of logarithms is if I have a logarithm of some argument and it's raised to a power, then the power of the argument can be moved down to become a coefficient. So this would become m times the natural log of u. That is not the same thing as if I raise an entire logarithm to that m power. There's no really properties that I can do to rewrite this guy unless you wanted to show that the natural log is being multiplied by itself several times. So you have to be very careful about that, and that hopefully the fact that those parentheses are around the entire logarithm helps that jump out at you guys. All right, so a couple more examples here. So speaking of that property, um, this one looks like it's a fairly complicated one where our u inside is actually the square root of x plus 1. And if we were to try and attempt this problem doing that, setting it up that way with u equals root of x plus 1, this would actually then need to be a double chain rule where the inside of that square root is x plus 1. However, you can do it that way, but it's going to make this problem way more complicated than it needs to be. Um, because this is a logarithm, remember what I just talked about, that power property with logarithms. If an entire argument is raised to a power, like say the 1/2 power, which is equivalent to taking the square root of a quantity, then that power can then be moved down in front and just become a coefficient. Again, if we do complicated algebra work before the calculus, it makes that calculus way easier for us. So now my u is simply x plus 1, and that derivative is super easy because it's just 1. So now when I rewrite this as 1/2 natural log of u, its derivative would be 1/2 times u prime over u, or u prime over 2u. So then my final answer here, once I've made my substitution back in, u prime is just 1 over 2 times x plus 1, or 1 over 2x plus 2. So anytime that you guys start with a logarithm with a radical inside, always rewrite it as that fractional exponent and then bring that down. So, especially with these logarithms, there's quite often a lot of extra work that we can do before we do the calculus to make it easier. Case in point, this crazy looking guy. This function, if I just went off of what it says right here, all of this stuff would have to be my u. That would require a product rule inside of a quotient rule, and part of that quotient rule would be a radical function, which is a complicated power rule. And all that stuff has stuff inside of it. There's like 15 different layers to this problem if you try to take the derivative right now as it's written. However, if you do some complicated algebra stuff before we do the calculus, it makes this problem way easier because this is actually a product and a quotient of three factors inside the argument of this logarithm, which means I can break all of this apart. This becomes the natural log of the first factor of the numerator plus the natural log of the second factor of the numerator minus the natural log of the one factor in the denominator, which is this radical. So by breaking it apart into all those pieces, now we have three separate problems, and we can actually do a little bit more simplifying with this. The first guy is just natural log of x. There's no properties that apply there. The second one, the argument is raised to a power, so I'm going to move the 2 down in front. The second, whoops, forgot to put the 1 back. The second one has a radical, so I'm going to rewrite that as this quantity raised to the 1/2 power, and then I can move the 1/2 down in front. So what I really am taking the derivative of is natural log of x plus 2 natural log of x squared plus 1 minus 1/2 natural log of 2x cubed minus 1. And again, if there are any lingering thoughts in your head about why am I not breaking this logarithm apart into x squared and 1 or this guy into 2x cubed and negative 1, remember the three properties are the power property, which you guys have seen used here, the product property, which you've seen used here, and the quotient property. There is no sum or difference property for logarithms. So when your argument has more than one term being added or subtracted, the only option you would have to try and break that apart is if you had an argument similar to this. If I had x squared minus 1, I could break that apart, but that is not because it's a difference. It's because that difference can be factored and rewritten as a product of two factors, in which case, yes, then you can break it apart and write them as separate logarithms. But that's not all the time. That is only when this argument can be factored. X squared plus 1 can't be factored. 2x cubed minus 1 can't be factored, at least not easily. So we are not doing anything more to these, and now we are ready to do the calculus. So f prime, we're going to try and do this one mentally. So I'm not going to write down my u's or my u primes like I would before. And another reason or another thing to keep in mind, if you had a problem like this where you had multiple insides, so this guy would need a u, this would need a u. Again, we don't like to use the same variable twice, so we could call this u and call that v if you wanted to do it that way. But we're going to do this mentally. First one, natural log of x, straightforward, no chain rule needed. That's just 1 over x plus, second guy, I've got a factor of 2 in front, constant multiple rule. Then again, I need the same structure of u prime over u. So my original inside goes in the denominator, and whatever its derivative is, since I already have it written here, I can kind of just look at it and take the derivative, and instead of writing down x squared plus 1 and then what the derivative is, and then putting it over here again, I just want to be a little bit more efficient with my time and your time. So I know looking at that, the derivative is simply 2x. So that's it. We'll simplify it here in a second, but mechanically that step is done. Second one, original inside. That original argument goes in the denominator. The derivative of 2x cubed is 6x squared, and the derivative of the constant is 0, so that's it. Now all I have to do is go through here and clean this up. So we get 1 over x plus 4x over x squared plus 1 minus the 1/2 and the 6 are actually going to reduce down to simply 3x squared over 2x cubed minus 1. Now, this is not, you guys aren't going to have a ton of these kinds of problems. You may see one or two of them pop up periodically. But if you wanted to condense this, the next step would then be trying to condense all this down into one fraction. So that is a lengthy process. To do that, we need a common denominator, in which case this common denominator would just simply be the product of all three of these denominators. So we're going to go through and multiply each one by what it's missing. So the first guy needs x squared plus 1 times 2x cubed minus 1. So when I multiply all that out, I get 4x to the fifth plus 2x cubed minus x squared minus 1. The second one needs a factor of x and 2x cubed minus 1. So this is really 4x squared that I'm distributing. So that becomes 8x to the fifth minus 4x squared. And add a little room here. And then the second one, or the last one, I need to multiply by x and x squared plus 1. So this is really 3x cubed that I'm distributing, or negative 3x cubed. So this becomes negative 3x to the fifth, and then minus 3x cubed. And then we just combine all of our like terms. Oops. So if we go through all of the fifth degree terms, go ahead and get the denominator written down here. So looking through, we've got 4x to the fifth plus 8x to the fifth minus 3x to the fifth. So that would be 9x to the fifth. Then we've got our cubic terms, 2 minus 3, so minus x cubed. Negative x squared, oops, forgot that one, minus 4x squared would be minus 5x squared. And then our one lonely little constant term of negative 1. Unfortunately for you guys, not every problem is going to be as fun as that one and have as many steps, but I'm sure you guys will survive with the ones you do get to do. All right, now for the very last one. So this is just, again, I mentioned it earlier, but these are the formally defined general forms for non-base E exponential and logarithmic functions. Again, they really work the same way as the other guys. They're just like e to the u or natural log of u, but we have those extra factors of natural log of the base. So for example, if I wanted to take the derivative of y equals 2 to the 3x power, my u would be the 3x, the thing that's different. U prime would be 3. So the derivative of y equals 2 to the u would be y prime equals natural log of the base, so natural log of 2, that's this guy, times the original 2 to the u, but then also times u prime. So in this case, we would get, now this is going to be a constant, so again, I don't like to multiply by constants at the end, so I'm going to move that out in front. So we get 3 natural log of 2 times 2 to the 3x. So you may see it left like this, but remember, this is a coefficient in front of a logarithm. So we can actually use that power property of logarithms in reverse. If I wanted to, and I do want to because it makes it look nicer, I can move that 3 back up top to become a power of the 2. So I can write this as natural log of 2 cubed, or natural log of 8 times 2 to the 3x. That's a much nicer and easier to look at and work with function than the previous line. All right, next one, y equals log of cosine of x. Remember, this is a common logarithm. When there's no a value written there, if it's missing, then it's really a base of 10. So this is base 10 log of cosine of x, so that's my u. U prime then would be negative sine of x. So y equals log base 10 of u. Its derivative would be u prime over u, but again, we have that extra natural log of my base written down there that we are dividing by. Again, for exponentials, we multiply by natural log of the base. Logarithms, we divide by. So then our u prime would be negative sine of x over natural log of 10 times cosine of x, or negative sine over cosine is really tangent. So this becomes negative 1 over the natural log of 10 times tangent of x. Oops, forgot my prime. There we go. And then for this last one, whoops, I forgot the y equals there. So log base 2 of this big ugly quadratic. Oops, so you have two options here. This guy actually does factor. So one option would be to rewrite this as log base 2 of the product of x plus 4, x minus 1. And if we choose to do that and then separate, it makes each derivative much simpler because now those inside functions have a u prime or v prime for the second one of just 1. So we could do that way. The downside of separating it like that is that afterwards you're going to have two fractions, and then we got to put them back together. So you could do it this way, but again, just like this one, it's not as difficult as this guy. But separating the logarithms will yield separate fractions, which then you in turn have to find a least common denominator for and put them back together. So if you want to do it that way, you can. I actually think in this case it would be a good bit simpler for us to just simply keep it as is and use our u prime over u trick, and just keep in mind we need that extra factor of natural log in the bottom. So I'm actually just going to treat this or do this guy with some mental math and write it out. So I know it's log base 2, so I know I need a factor of natural log of 2 in the bottom. And then my original denominator is down here, so x squared plus 3x minus 4. And then its derivative, now that I'm looking at it again, I know would be 2x plus 3. So you can see not separating it is actually going to be a good bit faster and easier to do here. This would still be the same result if you had ended up separating and finding a least common denominator, but this is a good bit more straightforward. We can kind of jump right from the original straight to the derivative. So that is it for the chain rule. Best of luck to you guys while you try these problems. And as always, let me know if you have any questions.